Good morning, friends. Welcome to today's session on acceptance rejection technique. So far, we have discussed about different types of inverse transformation, different types of distributions on which inverse transform technique can be applied, like uniform distribution, triangular distribution, Weibull distribution, exponential distribution, right? And in the last session, I have discussed few problems on empirical distribution and how we can apply inverse transformation technique on empirical distribution. So today's session will be on acceptance rejection technique, right? So this is the last topic in your third module. So in this topic, we'll be studying about how to generate Poisson variates. So acceptance rejection technique is basically applied for Poisson distribution. So the steps for generating the Poisson variate X uniformly, which is distributed between 1/4 and 1, is given by, here we are making use of uniform distribution, which is applied in the interval of 1/4 and 1/4 comma 1, right? There are three steps here. The first step is we have to generate a random number R, right? So step 2 is, if say for example, the random number R which we have generated is greater than or equal to 1/4, right? So if it is greater than the interval 1/4, then we will accept X is equal to R, because we want the numbers to be in the interval 1/4 to 1, right? So if it is greater than or equal to 1/4, we will accept that particular random number as our random variate, right? And then we go to step 3, right? So step 2b tells that if at all R is less than 1/4, if at all my random number is less than this particular interval, right, then I will reject R and I will return to step 1, right? So return to step 1 means we will be generating one more random number. Step 3 is if another random variate, right, so on the interval 1/4 comma 1 is needed, then repeat the procedure beginning again from the step 1, if not stop. That means if at all I need to generate for the random variates, right, so more and more random variates, then I have to go back to step 1, right? So otherwise I have to stop, right? So each time step 1 is executed, a new random number R must be generated. Every time we are executing step 1, a new random number R we have to generate. Step 2a is called as an acceptance and step 2b is called as the rejection, right? So that is why it is called as acceptance rejection technique, right? So I repeat, in the acceptance rejection technique, what we are doing, we are trying to generate the random variates, right, which are uniformly distributed in the interval of 1/4 and 1. There are basically 3 steps which are used in acceptance rejection technique. First, we have to generate a random number R. Then we have to check if at all R is greater than or equal to 1/4. Greater than or equal to 1/4 means it lies within the interval 1/4 to 1, right? So if at all it is greater than or equal to 1/4, then I will accept X is equal to R. So here we will not consider any number which is after 1, because our interval ends there, right? So our interval lies between 1/4 to 1. We know that uniform distribution is always between 0 to 1. Right? So if at all R is less than 1/4, then I will reject the random number and I will go back to step 1, right? So step 3 tells that if at all I want one more random variate, then I have to start the procedure once again from step 1. If not, I will stop. So each time step 1 is executed, a new random number R should be generated, right? And step 2a is called as an acceptance and step 2b is called as a rejection in this acceptance rejection technique, right? So the desired random variate X is uniformly distributed in the interval of 1/4 to 1, right? So we write that as probability of A is less than R is less than or equal to B, right? It's divided by 1/4 is less than or equal to R is less than or equal to 1, right? That means such that the interval A to B is written such that 1/4 to 1 is equal to probability of A is less than or equal to R is less than or equal to B. Probability of 1/4 is less than or equal to R is less than 1, right? So 1/4 to 1, right? So in general, we write it as B minus A divided by 3/4. Okay, so which is the correct probability for uniform distribution in the interval 1/4 comma 1. So if at all they ask you explain acceptance rejection technique, then you have to write what is this acceptance rejection technique, step 1, step 2a, 2b and step 3, and you have to stop till here, right? So this is the acceptance rejection technique, right? You need not write all these things. So if at all they ask acceptance rejection technique for Poisson distribution, then we have to see this, right? So coming to the next one, which is Poisson distribution. So a Poisson random variable n with mean alpha is greater than 0 has the probability mass function as, what is the formula for Poisson distribution? We know that it is e to the power of minus alpha into alpha to the power of n divided by n factorial, right? So it can be n or x factorial. So here I am taking probability of n, therefore it will be e power minus alpha to the power of n divided by n factorial, where n is equal to 0, 1, 2, etc. So the procedure for generating Poisson variates n is given by the following steps. What is the first step? First step is I have to set n is equal to 0 and p is equal to 1. Set n equal to 0, p equal to 1. Step 2, generate a random number Rn plus 1 and replace p by p into Rn plus 1. Okay, so we have to generate a random number Rn plus 1. That means take one random number, multiply it with the value of p. That means what I will get? I will get 1 into that corresponding random number. Step 3, I'll be checking whether my p value is less than e to the power of minus alpha, right? So if at all it is less than e power minus alpha, then I will accept n is equal to capital N is equal to small n, right? So if we solve the problem, you will understand what is this capital N is equal to small n. Otherwise, what I will do is reject the current n, increase n by 1 and return back to step 2. Otherwise, reject the current n, increase n by 1 and return to step 2. Upon completion, we'll be able to generate Poisson variates p is equal to phi of I equal to 1 to n plus 1 Ri. Right? So if at all p is greater than e to the power of minus alpha in step 3, then we have to, n is rejected and the generation process must proceed through at least one more trial. That means if it is less than e power minus alpha, if p is less than e power minus alpha, I will accept n is equal to small n, capital N is equal to small n. Otherwise, I will reject the value of n and I will go back to I will continue further with the next random number. Right? So if n is equal to n, then n plus 1 random numbers are required. So the average or the mean of the Poisson variates is given by e of n plus 1 is equal to alpha plus 1. So let us see the problems here, right? So with the problems, we'll be able to understand more clearly, right? So generate 3 Poisson variates with mean alpha is equal to 0.2. Generate 3 Poisson variates with mean alpha is equal to 0.2 for the random numbers r is equal to 0.4357, 0.4146, 0.8353, 0.9952 and 0.8004, right? So the solution, how to solve this problem is, first you have to calculate e to the power of minus alpha, right? So I will get it as e to the power of minus 0.2, right? So you have to make use of your calculators and find the value of e power minus 0.2 because alpha value is given as 0.2. Right, so in this problem, we have to make use of all these random numbers and I have to generate 3 Poisson variates, right? So we know that what is a random variate? A random variate is nothing but the outcome of a random number, right? So that's why using the random numbers only we can generate the random variates, right? So here we are generating Poisson variates, okay? Then what is the first step here in Poisson, in order to generate the Poisson variates, right? So we have to set n is equal to 0 and p is equal to 1, right? So same step I have written here. Step 1, set n equal to 0, p equal to 1. What is the step 2? Second step tells that generate a random number Rn plus 1 and replace p by p into Rn plus 1, right? So what we will do is generate a random number. So we have to take the first random number. What is the first random number? The first random number is R1 is equal to 0.4357. Right, so I have to take this random number R1 and I have to multiply p is equal to p into Rn plus 1. What is the previous value of p? It is 1. So 1 into R1. So 1 into R1 will be 1 into 0.4357. So I will write it as 0.4357. What is third step? Third step tells that if p is less than e power minus alpha, you have to accept it. If it is greater, you have to reject. Okay, so if p is less than e power minus alpha. So what is the value of p? 0.4357. I will check whether it is less than 0.8187. Right? We know that 0.4357 is less than 0.81.8, right? So I have to accept capital N is equal to small n. What is the value of small n? Small n is 0. That means I am able to generate the first Poisson variate at the point capital N is equal to 0. Right? So now, once again, what I have to do? I have to do the same procedure for the second random number, which is 0.4146. Right? So again, go back. Step 1, set n is equal to 0, p is equal to 1. right? Step 2 is take the next random number, right? Every time we are taking a new random number, so this will become R1, right? So R1, step 2 is 0.4146, right? So what I have to do in step 2, generate a random number, replace P by P into Rn plus 1. So P value is 1 into 0.4146, so I will get it as 0.4146. Don't take the value of P which is in the previous step, right? So we are doing the P only to whether we accept till we accept or till we reject, right? So if you are accepting, then that is one step which is completely independent in nature, right? So you should not refer to the previous step, right? So again you have to start from freshly, n equal to 0, p equal to 1, take the second random number, multiply it by the value of p is 1 into R1, we will get 0.4146. Again I have to check whether p is less than e power minus alpha. E power minus alpha is 0.8, here I have 0.4, 0.4 is less than 0.8, so again I will accept capital N is equal to small n. What is the value of n? N is 0. So capital N is equal to 0. I am accepting this number as the Poisson variant. Again, step 1, set n equal to 0, p equal to 1. Take the third random number. What is the third random number we have here? It is 0.8353. Right? So take the random number. It is 0.8353. So p will be equal to p into Rn plus 1. Right? So that will be equal to 1 into 0.8353. So I'll get it as 0.8353. Right? So then I have to check whether p is less than e power minus alpha. What is the value of e power minus alpha? We had 0.8187, right? So 0.8187 is not less than 0.83, right? So that means p is greater than e power minus alpha here, because p value is 0.83 and e power minus alpha value is 0.81. So 0.83 is greater than 0.81. At that time, what I have to do? I have to reject the current value of n, right? So reject n is equal to 0 and go back to step 2 by incrementing n, right? And return to step 2 with n is equal to 1, right? So I'll be going to the second step by incrementing the value of n. So small n becomes 1 now, right? So what I will do, I'll take the next random number. What is the next random number here? I have 0.9952, right? So I will take that particular random number 0.9952. Again, I will multiply p by p is equal to p into Rn plus 1, right? So since I am rejecting, I will take the previous value of p. If you are accepting, then you have to stop, right? So whenever you are rejecting, you should take the previous value of p. Why we are doing this? Because if we multiply, then I will be able to reduce this value and we can accept it, right? So you can see here, we have to go back to this step. We have to multiply this 8353 with 9952. So p will be equal to R1 into R2, 0.8353 into 0.9952. I will get it as 0.8313. Once again, I have to check whether p is less than e power minus alpha or it is greater than e power minus alpha. If p is greater than e power minus alpha, what I will do? I will reject n is equal to 1. Again, reject n is equal to 1 and return to step 2 with incrementing the value of n. Right? So n is equal to 2. I repeat, we started with n is equal to 0, p is equal to 1. We took one random number, multiplied with the previous value of p, because until here we had acceptance, right? So once it is accepted, we have to stop. If at all it is rejected, then only we should continue. Okay, so I will get 0.8353. Now 0.8353 is greater than 0.81. So I have rejected n is equal to 0 and return to step 2 with n is equal to 1. Right. So now we are incrementing the value of n by 1. So once again, I will take the next random number in the problem. In the question, they have given it as 0.9952. So now I have to multiply this 0.9952 into 0.8353. I will get the answer as 0.8313. Right? So now we have to check this 0.8313 whether it is greater than e power minus alpha, whether it is less than e power minus alpha. Since it is still greater, what I will do, I will reject the current value of n. What is the current value of n? N is equal to 1. Right? So reject the current value of n and return back to step 2 with incrementing the value of n. So n becomes 2 now. Now I will take the next random number. What is the next random number? 0.8004. Right? So I will take the third random number R3 as 0.8004 and p will be equal to R1 into R2 into R3. Right? So you have to multiply R1 into R2 into R3. That means R1 into R2 you have multiplied, you got it as 0.8313. Now multiply that 0.8313 into 0.8004. Right? So if you multiply, you will get the value as 0.6654. Right? Now we have to check whether this particular value is less than e power minus alpha. Right? So 0.866 is less than 0.81. Therefore, I will accept n is equal to capital N is equal to small n. What is the current value of small n? Small n current value is 2. Right? So accept capital N is equal to 2. Like this, you have to solve the problem on acceptance rejection technique. Right? So summary is very simple. we will write Poisson variates as capital P. Small n is the value of n. Rn plus 1 is the random numbers. Accept or reject, what is the result? Right. So what is the first random number? Right. So in this column, we'll be writing the random numbers which are given in the question. The first random number was 0.4357. Right. So initially, what is the value of n? Initially, the value of n was 0. N is equal to 0. Right. So n is equal to 0, and the first random number was 0.4357. We can see here. The first random number is 0.4357 and n is equal to 0. What is the value of p I got? P value I got it as 0.4357, and here p is less than e power minus alpha. So accept small n, capital N is equal to small n value, which is 0. Right. So whatever we did, we are just writing the summary. Right. So here the first random number was 0.4357. N value was 0. What was the p value? P is also equal to 0.4357, and we have accepted the value as capital N is equal to 0. Same thing is written, right? So now write for the next random number. What is the second step we did? For the next random number, again our n value was 0. What was my p? P is equal to 0.4146. Random number is also 0.4146. Since it is less than e power minus alpha, again I have accepted capital N is equal to 0, right? So 0.4146 is the random number, right? So small n value is 0. For Poisson variate is 0.4146. P is less than e power minus alpha, so accept n is equal to 0, right? So now coming to the third step, what we did in the third step, we took one more random number, right? So what is the random number? 0.8353. What was the value of p? 0.8353. We rejected it, right? So 0.8353 value of n was 0. Value of p is 0.8353. Since it is greater than e power minus alpha, we have rejected. Then what did we do? We incremented the value of n by 1, right? So n is equal to 1. What was the next random number? 0.9952. What was the value of p? We multiplied 8353 into 9952. We got it as 0.8313. Right? So again we got p is greater than or equal to e power minus alpha. So again we rejected. In this step also we have rejected when it is 0.8313. Right? So next what we do? We will take the next random number, the last random number, which is 0.8004. Then we multiplied this 0.8313 with 0.8004. We got the value as 0.6654, right? So the value of n is 2. What did we do? Right? When n is equal to 2, that is small n is equal to 2, right? So we accepted it because p is less than e power minus alpha. Capital N is equal to 2, right? So you have to write this summary here because summary is very, very important. They will not check the individual step in the exam. They'll be referring to this particular table. Right, so it took 5 random numbers for us in order to generate 3 Poisson variates at capital N is 0. We have accepted. Capital N is equal to 0 also we have accepted, and capital N is equal to 2 also we have accepted. Right, so at the N is equal to 0, 0 and N equal to 2 we have accepted. But say for example in the long run we have to generate 1000 Poisson variates with mean given as alpha as 0.2, then how many random numbers are required? If at all they ask you how many random numbers are required in order to generate 1000 Poisson variates, means we have to make use of this formula, right? So 1000 into alpha plus 1, right? So because we had the formula for mean here, E of n plus 1 is equal to alpha plus 1, right? So same thing I'm doing here. 1000 into, I have to multiply that n, 1000 into alpha plus 1. What is alpha? 0.2. 0.2 plus 1, I'll get it as 1.2. 1.2 multiply it with 1000, I will get it as 1200. 1200 random numbers are required in order to generate 1000 Poisson variates. So in your exam, they will ask the question like this: what is acceptance rejection technique? Generate 3 Poisson variates with mean alpha equal to 0.2 and the random numbers they will give, right? So we have to solve like as shown. So if they ask what is acceptance rejection technique, write both acceptance rejection technique and acceptance rejection technique for Poisson distribution also, right? So same previous problem, follow the same steps, right? So we'll be able to get the answer for this particular problem, right? So initially it will be accepted, right? So this is how you will get the solution of the previous problem, right? So let us see this problem also. Initially we started with set n equal to 0 and p value as 1. What was the first random number? First random number we took, right? So it is 0.4357, right? So you accept. 0.4146 also you will accept. 0.8353 is where you reject, right? So solve this particular problem, right? And you will get the final answer. So one more problem is there. Explain acceptance rejection technique for Poisson distribution. If they ask specifically this, then you can directly go for acceptance rejection technique for Poisson distribution. Generate 5 Poisson variates with mean alpha equal to 0.25 given the random numbers. Right. Solve these problems at the last of your notes. Right. So previous year question paper problems are given LCM. Right. So all this try to solve them. Right. I'll be try to solve them, and you can call me or message me if you have any doubts with respect to all these problems. All these problems are based on your linear congruential method and your combined linear congruential method, Kolmogorov-Smirnov test, chi-square test, right, autocorrelation test, and also your Poisson variates, which is acceptance rejection technique, right. So and below the at the last, as the last pages of the at the end of the notes, right, you can find your Kolmogorov-Smirnov critical values. All these are values which are taken from your simulation textbook, right. So at the end we have simulation table, right. So there we have all these critical values which will be made use of in our problem, right. So you have seen that we have used this chi-square distribution in order to solve chi-square problems. We have also used the Kolmogorov-Smirnov critical values in order to find the in order to solve the problem on frequency test. That means uniform distribution on Kolmogorov-Smirnov test in order to check for uniformity, right. So we have used this particular table, right. So this completes your third module. Thank you.